Hello, everyone. I'm a PhD student from Chalmers in Sweden, and my name is Yong. So I'm glad to present my work at Chalmers. My work is to generate an iron diamond microwave photon. To achieve that, I prefer to introduce you some background about lights. The lights are very popular and everywhere. So outside the rooms, we can enjoy the sunshine. Sunshine is very important for plants, animals, and human beings. At night, we can also see a lot of lights with different colors along streets. So sometimes we can also see some lights from lasers. So here we have 3 lasers, and they can generate light beams with different colors. This is green. This color is red, and this is pink color. And different with lights from sunshine and lamps. Lights from lasers have certain wavelengths. So a light can be described by waves, a continuous wave. For example, this wave, this pink color has a wavelength from peak to peak is about 400 nanometers. And when we change the length, the wavelength of the light, then the color is also changing. Besides the visible lights with wavelengths in the range of several hundred nanometers, we also have some invisible lights around us, such as gamma rays, X-rays, and microwaves. Here, we are interested in microwaves. So its wavelength is on the order of micrometers, corresponding to a gigahertz frequency range. To understand the range of light, we look at a laser. So in a laser instrument, the most important element is a material consisting of a lot of atoms. So here, each cycle represents an atom. Inside the atom, it has different states. The atom status will be different. Here, we just simply consider an atom as a 2-level system. This is 1 level, ground level, and this is the 2nd level, regarded as an excited level. So now all the atoms are populated, and then they will emit photons at a certain frequency. Then we will have lasers at output of laser instrument. Now let's pick up a single atom from this material. If we put a button on top of this atom, then we can use this button to control the state of the atom. When the button is off, the state of the atom is at ground state. When the button is on, the state of the atom is changed. Afterwards, this atom emits a photon into space or a waveguide. In the microwave domain, we need a waveguide to guide the propagation of the waves. Now, if we click the button again, so we will have a second microwave, a second photon from the atom. You click again, we'll have the third one. We can repeat to click the button to let the atom to emit a photon continuously and repeatedly. So depending on the energy distance between the ground state and the excited state, we will have different frequency domain. So basically, in our case, we need to generate a microwave single photon source, which is in the gigahertz frequency domain. Now, so I would like to emphasize that, and a single photon is the fundamental element of lights. So when we say laser beams, sunshines, and lamps, and the lights from lamps, they typically contain a lot of photons, a lot of individual photons. Okay, so now the most important thing for obtaining a microwave single photon source is to get an atom. How to get such an atom? So in our case, we fabricate this atom in a standard clean room. Here we firstly evaporate some aluminum on the top of the substrate. And this aluminum forms a ground plane. And then we evaporate aluminum electron, which is a cross shape. And it will give us some inductance between this cross shape and the ground plane. Then we fabricate such a loop. So here we can see a loop, and we have some small collection between this arm and this arm. And this collection is this corresponds to this. This one is this one. So this loop is an inductor, but it's different with normal inductor. This inductor is linear, nonlinear, and the inductance will depend on the current through the inductor. Moreover, if we send the magnetic flux through this loop, the inductance will be also changed. So now we have an anharmonic LC circuit. This is a capacitor. This is an inductor. The different with a normal LC circuit. So here, this LC circuit will give us a two-level system. Then we can use it as an artificial atom. As soon as we have such an atom, so we let this atom couples to a waveguide. And the waveguide is also made of aluminum. So it can be used for collecting the emission from this atom by capacitive coupling. Okay, now we have waveguide and we have atom. Moreover, this atom frequency can be changed, as I mentioned. And when we change the magnetic flux through this loop, the inductance of the atom is changed. Then the frequency of this atom is also changed. I would like to say the atom size is small, on the order of several hundred micrometers. Okay, we have atom, we have waveguide. How to click the atom? To click the atom, we need another microwave component. Here we have a microwave component which can be regarded as a beam splitter. Typically, if we send a signal into this microwave component, most of the signal will be transmitted. However, some of the signal will be sent into the waveguide to click the atom. As soon as the atom state is flipped, and then the atom will emit a photon into waveguide in the microdomain. So finally, we can observe a single photon at output of this microwave component. Okay, what can this system be used for? And let's consider the two states of the atom. When the atom is at ground state, we can encode information 0. However, we will get information 1. Then, if we collect these two atoms together, when this atom is excited, it will emit a microwave photon into the waveguide. By propagation inside the waveguide, this single atom will be also absorbed by this atom. And then the state of this atom will be changed. So we can use this system to transfer information from one atom to another. And finally, we can build up a quantum network. Thank you for your listening.